Hello, our dear students and teachers. Previously, we have tried to see about fluid statics. We have tried to see about Pascal's principle and Archimedes' principle. We have also tried to see main terms like liquid pressure, atmospheric pressure, and absolute pressure as well. And today we will try to see about fluid dynamics. And under fluid dynamics, we are trying to deal that there will be a fluid, might be liquid, passing through a conduit or container, so that we are trying to see about the property or characteristics of such kinds of fluids. So here we are going to deal about fluid dynamics. Fluid dynamics is the study of flow of fluids through pipes, or it might be channels. And as fluids flow through pipes, there can be different types of flow. There will be a turbulent flow or irregular flow, or there might be a streamline or a laminar flow, a uniform flow of fluids. We mainly focus on a uniform flow of fluids, okay? There might be, but a turbulent flow. And here we have main terms needed to discuss about fluid dynamics. And this term is known to be flow rate. We call it to be flow rate, and it might be symbolized as Q. Sometimes flow rate is known to be discharge, or it might be known also as charge, okay? And flow rate can be mathematically given or measures the amount of flow of fluids per unit time, and the amount of fluids is measured in volume. Flow rate can be mathematically expressed as volume V over time T. And its SI units, the SI unit of flow of rate or discharge or charge can be given as the SI unit of volume over the SI unit of time. The SI unit of volume is meter cube over time is second. And we know that on a given conduit or a pipe here, there will be flow of fluids through here, and the multiplication of cross-sectional area of the pipe to that of the length of the pipe gives us volume. Volume can be expressed as area times length L. So instead of using the volume V, you might use area times length L. So area times length L, when you substitute area times length L over time T. But the rate of change of this length to that of time T. You can say length to time T, or displacement S over time T. The rate of change of displacement to time T is known to be velocity, or we can take it as speed. So length to time T is speed V. We can express this flow rate as area times speed V. Here it says capital V, meaning volume, but here it says small v, meaning speed or velocity of the water. Therefore, flow rate can be given as area of cross-sectional area of the pipe times the speed V can be given as flow rate Q. This is how we represent flow rate, and it's very important term. And under fluid dynamics, we have two important laws, and these laws are known to be the law of continuity and Bernoulli's principle. And here, let's try to see about the law of continuity. Actually, the law of continuity is derived from the concept of conservation of mass. Mass is neither created nor destroyed. So that the amount of the mass that you insert here is the same as the amount of the mass that's going to be collected here, meaning the amount of the volume of water per unit time t is the same as the amount of water per volume per unit time t here. And this law is known to be the law of continuity. And the law of continuity is all about the flow rate remains at any section of the pipe remains constant. The flow rate always remains constant. It said that the flow rate at this section, call it Q1, and the flow rate at this section is Q2, is all the same. From the concept of mass, the mass at 1 is equals to mass at 2, and mass can be expressed using density is given to be mass over volume. From this, mass can be expressed as density times volume. So density of the object, volume of the object is equals to density of the object, volume of the object. Let's say in this case the water. Density of the water at specified point over, let's take per unit time t, per unit time t. The density at section 1 and density at section 2 remains constant because density of water here as well as water doesn't change. Okay, we are mainly talking about highly incompressible fluids is not included here, but we are mainly focused on the fluids that has a slight compression, so that their density remains constant. So the volume per unit time t at section 1 should be equals to the volume per time t at section 2. And volume per unit time t is known to be flow rate. Previously I have mentioned that it is flow rate. So flow rate at section 1 should be equals to flow rate at section 2. This is a concept and it is derived from the law of conservation of mass. And we have also expressed flow rate as the multiplication of the cross-sectional area times the speed of the fluid as it passes through those cross-sectional areas. So in this case, flow rate at section 1 can be given as area 1, the cross-sectional area 1 times the speed of the water at point 1 should be equals to the multiplication of area 2 times the speed at point 2. This is flow rate at section 2. From the concept of law of continuity, when you equate these two equations, area 1, speed 1 is equals to area 2, speed 2. This concept is known to be the law of continuity. It is fundamental law in fluid dynamics. Here we have one example. We can solve this. It says that water flows through a fire hose of diameter 6.35 centimeter at a rate of 0.12 meter cube per centimeter. The fire hose into a nozzle of inner diameter to be 2.2 centimeter. Okay, what is the speed within which the water exits the nozzle? So they say that we have a nozzle. This is a nozzle, and then the hose ends up with a nozzle. Here you have a hose. And the diameter of the hose is given to be 6.35 centimeter. This is the diameter of the hose, 6.35 centimeter. And the hose ends up to that of a nozzle. The diameter of the nozzle, D, let's say D2, diameter 2, is found to be 2.2 centimeter. 2.2 centimeter. And the flow rate is given to be 0.12 meter cube per second. Flow rate Q is 0.012 meter cube per second. Now the question is, what is the speed within which the water exits the nozzle? As it exits the nozzle, what is the speed? V2. Okay, and we don't know the speed here. The hose doesn't give. Therefore, the only concept that we have is the flow rate. We know that the flow rate at section 1 and at section 2, meaning in this case at the hose and at the nozzle, remains constant. Therefore, flow rate at section 2, Q2, can be given as area 2 times V2. And at section 1, it's possible to have at section 1 area 1 V1. we can equate these two equations so that we can find the velocity or the speed of the water as it passes through the nozzle. Area 1 V1 should be equals to area 2 V2. Therefore, area 1, since it is a circular path, it's possible to have area of a circle can be generally given as pi r squared, or it's possible to have pi d squared over 4. This is how we determine area. The hose has circular cross-sectional area as well as the nozzle has circular cross-sectional area, pi d squared over 4. In this case, for the hose, it's possible to say pi, the diameter is already given to be pi d1 squared over 4. V1 should be equals to area 2. The area of the nozzle is given to be pi d2 squared over 4 times V2. So pi over 4 can be cancelled, and V2 and V1 can have a relation. So V2 is equals to, we can have d1 over d2 the whole squared times V1. It's possible to have a relation. We know that d1 is given to be 6.35, whereas d2 can be given as 2.2, so that taking the ratio squared, we can have a relation between the velocity of the fluid as it passes through the hose and the velocity of the fluid as it passes through the nozzle. Still, we didn't find V2, but we have one good way to find that. We have a flow rate. The flow rate at any section, it might be at the hose, it might be at the nozzle, remains constant. Depending on the law of continuity, it says that flow rate remains constant. Therefore, taking this, it's possible to have Q is equals to area times V. We are trying to find the velocity of the fluid at the nozzle. The flow rate is given to be 0.012, and the area at the nozzle can be given as pi d squared. The diameter of this one is given to be d2 squared over 4. This is how we determine the area of the cross-sectional area of the nozzle times the velocity V2. Okay, V2. So it's possible to find the velocity V2 using this concept as 31.6 meter per second. It's possible to have such a relation, so that keep this in your mind. Now let's proceed and try to see the second law under fluid dynamics, and that law is Bernoulli's equation or Bernoulli's principle. Actually, this principle is not a new law. It is derived from the concept of law of conservation of energy. It was proposed by Daniel Bernoulli, Austrian physicist, and it states that the three quantities on different sections remains constant. What are those three quantities? Actually, in different books there are different names, but here we can take that the sum of pressure head, velocity head, and the piezometric head always remains constant at any section of the pipe. Here if you have a pipe which contains a uniform or laminar flow of fluids through this, at any section, you might take at point 1 here, point 2 here, point 3, at any section, the summation of these three quantities always remains constant. And this concept is derived from the law of conservation of energy, meaning the energy at this section is equals to the total energy at this section. We can take point 1 and point 2. At point 1, mechanical energy at point 1 plus the work done by different in pressure. Here we have pressure P1, here we have another pressure P2, oppositely acting, so that due to the difference in pressure there will be a work performed, so that there will be mechanical work as we go from point 1 to point 2 is equals to mechanical energy at section 2 or point 2. And we know that kinetic energy is the sum total of potential energy and kinetic energy. Mechanical energy means kinetic energy at section 1 plus potential energy at section 1 plus work done due to pressure difference is pressure 1 minus pressure 2 times the volume V. Okay. is equals to section 2 is kinetic energy at section 2 plus potential energy at section 2. Suppose here you have a frame of reference. The elevation or the height of this object is measured from this. Let's say at section 1 we do have h1, and here at section 2 you have h2, and the speed of the water as it flows through this cross-sectional area is v2, and the speed of the water at section 1 or point 1 is v1. And the cross-sectional area can be given as a1 and a2 and so on. Kinetic energy is energy due to motion, so that we can take 1 over 2 mass times velocity v1 squared plus, we know that the potential energy due to the weight of the fluid can be given as mass times gravity g times h1. We can say h1 because this section is found at elevation 1. And the pressure difference enables us to perform work. It's possible to have P1 minus P2, but instead of volume, either the volume here and the volume here, the volume can be expressed in terms of density, mass and density. We know that density is equals to mass over volume, so that volume can be expressed as mass over density. So we can express it as mass over density here is equals to kinetic energy at section 2 can be given as 1 over 2 mass times the velocity at point 2 squared plus the potential energy due to the weight of the fluid can be given as mass times gravity times h at section 2. Here you do have mass as well, here mass, and there is mass at every section. We can eliminate on both sides since we do have mass. And the result becomes v1 squared over 2 plus, since m is cancelled out, g times elevation at section 1. We can take this density as plus P1 over rho minus P2 over density rho is equals to, since m is cancelled again, on this section we have V2 squared over 2 plus, here since mass is cancelled out we do have gravity times gravity plus gravity times 2, h2, elevation h2. So here v1 squared over 2, g times h1, p1 over rho g. Here let's transfer this to the other side. When we are transferring this to the other side, we can have such an expression. We know that v1 squared over 2 plus g times h1 plus pressure 1 over rho. As you transferred it, this pressure 2 over rho, this is negative, so that when you take it here, it will be positive, is equals to v2 squared over 2 plus g times h2 plus pressure p2 over rho, density of the fluid. Now look, v1 at section 1, the velocity at section 1, elevation at section 1, pressure at section 1 is the same as v2 over 2 at section 2, elevation at section 2 and pressure at section 2. And this tells us that velocity v squared over 2 in generally plus g times h plus pressure p over density rho at section 1 is the same as at section 2. Meaning at any section, if you are trying to multiply, to add those three variables, meaning v squared over 2, gh and so on, if you are trying to add all those three quantities, remains constant. It remains constant at any section. So this is what we call Bernoulli's principle. It says pressure P, it's possible to multiply all side by density rho. If you are trying to multiply using density rho at here as well as here, you can find that v squared, density times v squared, 1 over 2, density times v squared. Then if you are trying to multiply density with this, rho gh, or it's possible to cancel rho by rho so that we can have pressure P. So pressure P plus half of density of the fluid times velocity squared plus density of the fluid, gravity times elevation, is always remains constant, meaning at any section, here you have section 1, here another section, here another section. At every point, if you are trying to add all those three quantities, it remains constant. This is what it says, Bernoulli's principle states. Or it's possible to have the same expression in terms of pressure P over rho g. You can divide both sides by 1 over rho g. So we can have pressure over rho g plus v squared over 2g plus h is constant. In this case, we'd have a name for each variables. Here, it's possible to say that pressure over rho g is known to be pressure head. It's also possible to have v squared over 2g. V squared over 2g is known to be velocity head. As the name implies, it says velocity head, and h is a piezometric head. So piezometric head plus velocity head plus the pressure head remains constant at every section of the pipe, the conduit or a pipe. This is what we call Bernoulli's principle, and it's a law of conservation of energy. It's derived from the law of conservation of energy. It's not a new law, but it is a rearrangement of equations. Keep this in your mind. And now let's try to solve one good example concerning on Bernoulli's principle. Here it says there is a horizontal pipe of 10 centimeter in diameter, has a smooth reduction to a pipe, to another pipe which is 5 centimeter in diameter. If the pressure of the water in the larger pipe is 80 kilopascal, and the pressure in the smaller pipe is found to be 16 kilopascal. At what rate does the water flows through the smaller pipe? This is what it says. At what rate does the water flows through the smaller pipe? You can express this figuratively as we'd have two pipes, and those pipes, it says a horizontal pipe. Okay, it says horizontal pipe. Previously, when we are trying to determine a pipe, there is a pipe which gradually increasing and found at different elevation or level. But in this case, we can take a horizontal pipe. You can have a horizontal pipe here. The diameter of the pipe is gradually reduced into smaller reduction to another pipe. Let's say that the diameter of the smaller pipe be D2, the diameter of the pipe 1 or the larger pipe B, D1. It says 10 centimeter and 5 centimeter. Okay, this one is 10 centimeter, the larger one is 10 centimeter, the smaller is 5 centimeter. Then what happens? The pressure exerted on the larger pipe is 80 kilopascal, and the pressure which opposes at the smaller pipe is 60 kilopascal. Here it says we have pressure P1 to push that water is P1, and there will be a pressure exerted here P2. The pressure exerted at P1 is 80 kilopascal. Let's call it to be P1. And the pressure here is 60 kilopascal. And the other quantity given here is the density of the fluid is known to be water, so that at what rate does the water flows through the smaller pipe? This is a question. At what rate does the water flows through the smaller pipe? V2, we can call it V2. Here you have the water flows at a rate of V1. So how do we determine the speed V2? We can apply the concept of Bernoulli's principle. Let's say that it is found at elevation H1 here, H1, as well as it is found at elevation H2. Since it's a horizontal pipe, the elevation H1 and H2 remains constant. Okay, so the three quantities previously mentioned in Bernoulli's principle, the three quantities, the summation of three quantities here and here are all equal. What are those three quantities? Well, the three quantities are the pressure P over rho g at section 1 plus the velocity V squared over rho g 2 times g, okay, plus elevation H is always remains constant. The pressure head, the velocity head, and the piezometric head remains constant. This is what the Bernoulli's principle states. But if you are taking the larger pipe as 1, let's say that pressure 1, velocity V1 squared, H1 is equals to pressure P2 over rho g plus V2 squared over 2g plus the elevation H2. But in this case, since the pipe is horizontal pipe, H1 and H2 are equal. So we can eliminate these two. What we are asked is to find the velocity V2, okay? Therefore, we can have P1 over rho g plus V1 squared over 2g is equals to P2 over rho g plus V2 squared over 2g. This is the equation left. We are asked to find this. Let's transfer this to this side. So P1 over rho g minus, okay, P2 over rho g plus V1 squared over 2g is equals to V2 squared over 2g. So to find the velocity V2, we should have to multiply both sides by 2g. 2g here as well as 2g here. So 2g will be cancelled by 2g. When you are trying to cancel, here we have left that velocity at section 2 squared. But here when you are trying to multiply this each by 1, 2g with this, you can eliminate gravity so that, okay, we have 2 P1. You can cancel out gravity over density rho. When you are multiplying this by this, you can cancel again gravity by gravity minus twice of P2 over rho. And if you are trying to multiply 2g by 2g, you can cancel out this, and you have left with V1 squared is equals to V2 squared. V2 squared. So here we have pressure P1. Okay, good. We have pressure P2, 60. But we don't have velocity V1. To find velocity V2, we don't have velocity V1. So how do we determine velocity V1? Or how do we relate V1 and V2? So to correlate V1 and V2, remember that there is another law known to be the law of continuity. In the law of continuity, we know that flow rate at section 1 should be equals to flow rate at section 2. At section 1, it says area 1 V1 is equals to area 2 V2. So area 1, since it's circle, we can have pi d1 squared over 4 times V1. This is area of pipe, larger pipe. And here you'd have pi d2 squared over 4 times V2. So we can cancel these two. D1 is 10 centimeter and D2 is 5 centimeters, so that we can have D1 over D2, the whole squared, times V1 is equals to V2. So V1 and V2, they can have such kinds of relation. D1 is 10 centimeter over D2 is 5 centimeter. Actually, here we can convert it into meter, then you can find it, or you can put it in centimeter because it will be cancelled out after all. So squared times V1 is V2. So V2 gives us 10 divided by 5 is 2, 2 squared is 4, 4 times V1. So we can find a relation between V1 and V2. So instead of V1, you can have it to be V1 is equals to 1/4 of V2. So we can substitute here as 1/4 of V2, the whole squared is equals to V2 squared. So all the quantities are given here. Pressure P1 is 80 kilopascal. Pressure P2 is 60 kilopascal. Here, instead of using V1, we have an expression in terms of V2. We can transfer it to the other side. 2 over rho P1 minus P2 into or equals to. You can transfer this to the other side so that V2 squared minus 1 over, as you squared 4, you can have 1 over 16 V2 squared. So V2 and V2 are all the same. We can take it as a common and find the answer. So the answer, as you try to calculate, you can find the answer it to be 6.53 meter per second. This is the rate of the water flows as it passes through the smaller pipe. So this is all that I've got for today. You can have different problems. You may solve such problems here. So that's all that I have got for today. And that's the end of our revision period or revision program. Next time we'll try to see, might be meet on some other topics. So that's all, and I wish you a good studying case and national exam, and goodbye.